Sorry.
My name is Araya Faraz, and I would love to explain the concept of Newton's laws of motions with my car, Emrod. First, let me start by explaining the two laws I'm going to focus on. Newton's second law, which states, relates the acceleration of an object to the vector sum of all the forces exerted on that object. In other words, Newton's second law lets us relate the concept of acceleration to the sum of forces an object exerts. Now we can use this formula to use the mass and acceleration to find the sum amount of forces. But why is this helpful? Well, what if we wanted to know the acceleration Emrod experiences when she's carrying a heavy load up an incline and are given both the mass and her sum of forces? You could easily change the equation around using algebra to solve for it. So here we can see sum of forces equals mass times acceleration. This is great because it lets us relate acceleration here using forces to acceleration here in kinematics. Yay! So, what I was talking about when you manipulate something algebraically, so if we were given Emrod's mass, if we were given her mass, and we knew her sum of forces because we were given that in a problem, it's as simple as dividing mass, and now you have acceleration. Now you have a whole new equation that you can work with. Sum of forces, in this case the y direction, over mass. Now, here I've designated sum of forces in the x direction and the sum of forces in the y direction. Now, this is another factor that will come with x and y coordinates and vectors, so I'll give you kind of an idea. So if we have x and y here, right? X here, y here. So if we have the acceleration in the y direction, which is usually this part right here, sometimes it's the height, sometimes it could be anything. Maybe you're given that, right? A lot of times we could potentially use gravity, so 9.8 acceleration due to gravity over meters per second squared. And that's a value that we can use. And sometimes we're given mass. Any manipulation of this is really helpful. And again, the other part, it's the same way with the x direction. So if I were to draw out the incline, right? Say I have Emrod, my car, right here. That's Emrod. And she's driving up an incline. We're going to do our coordinate system again, here and here, right? So if we're saying this, she's coming from the negative direction, positive direction, and she's going up an incline at a degree, at an angle, some angle, right? And we know her mass equals some value in kilograms maybe, and we know this angle is what? Now what we can do is we can break this problem into components, and we can figure out Emrod's sum of forces. Yeah. Cool. So the other law that I'm going to talk about is Newton's third law, which states, unlike the first two Newton laws of physics, the third law deals with two objects working together. The third law states if two objects, A and B, interact, the force exerted by A on B is equal in magnitude to the force exerted by A, but in the opposite direction. In other words, the reasons humans do not float away from Earth is because of Newton's third law. So I'm going to show that with Emrod here again. So the reason that Emrod doesn't float away, yay, no, is because of the force of gravity holding her down, right? The force, let's do on by. So the force on Emrod by the Earth, pulling her down toward the center of the Earth, is counteracted by opposite force equal an opposite force, which is the force, which is the normal force, but in this case we're going to do on by again. Forces on M-Rod by the road. Okay, well, what does this mean? This means that the same amount of force that M-Rod is being pulled down is the same that is being, the same as she is being held up by the road, right? So say there's 10 newtons here, 10 newtons worth of force, pulling her down towards the center of the earth. There's also 10 newtons holding her up so she doesn't go anywhere, right? So this is why based on our force equation, some people think that the bigger your car is, right? Say you have a big mass, right? But you have a little acceleration. Your sum of forces is still pretty big, right? The same can be said if you flip it. If you have a big acceleration, if you're going really fast, but you have a little mass, say you have a Prius, or sum of forces. See? Yep.